So this is the algorithm that I gave you guys. The backtracking with recursion algorithm should hopefully be pretty familiar to you guys right now. So I'm going to assume that you've read this and have tried to solve this on your own, okay? So the big thing here is the hints I gave you earlier in the other videos were saying, so we've got this 8 queens problem that we are going to place 8 queens on the chessboard so that none of them capture one another. Now what I'm going to do is I'm going to run through this algorithm on the board, on a 4x4 chessboard, right, so to speak, okay? So this algorithm over here is one that we adapt based on the circumstances, right? And it says that if the position is such that there's nothing left to solve, we return true. That means essentially if we go off the board, if we get to a point that basically we filled in the last square or whatever, we're done, and we'll return true. And what we'll see is that sends a cascade of return trues all the way back up to the original caller. Then we have for each possible choice. If it's a valid choice, mark the position of the board at position with choice. And if you can if solving that board and the next position returns true, then we return true. If it returns false, then that means that something went wrong somewhere. Okay? And at some point, you have to clear the choices you make on the board. So I'm going to go ahead and draw my board. And yeah, it's going to be small to see, but I think the algorithm is a bit more important. So I'm going to just draw a 4x4 board. Right? That crack in there actually, we'll use it. So 1, 2, 3. So this is less of an 8 queens problem, more of a 4 queens problem. Now in this problem, as I mentioned, position means different things. In Sudoku, you have 2 variables, the row and column. Here, you just need one thing, which is the column, because we know we can only put 1 queen per column, right? So if we limit our problem to if for each queen, for this particular queen, what row sheet should she be in, then that makes it a bit easier. So let's go through it. First, is my position such that there's nothing left to solve? No, it's not. Right? I'm in this column. I need to find a place to put a queen there. So for each possible choice, what are my choices? My choices are the rows that I have available to me. So is this a valid choice for where I can put a queen? Well, there's no other queens on the board, so I'll put a queen there. Okay? So I put down the queen, and then I call solve board pos +1. Okay? Is that equal to true? Okay, so well, first thing I need to call, so now I'm going to call solving on column 1. So is this a valid choice? No, it is not. And how do I know that? Well, I don't check above and below me, right? If I'm trying to put a queen here, I'm looking at this particular row column combination. Okay? So do I need to put a queen here? No. I can't. I know that from I don't have to check above. I don't have to check below because only 1 queen per column. I also don't have to check in this direction, or my upper diagonal to the right, or my lower diagonal to the right, because if I'm moving from left to right, then there's going to be nothing to my right. Right? So I only actually have to do 3 checks. Is there another queen over this way? No, because it's out of bounds. What about this way? Well, I found a queen checking all the spaces to my left, so I can't put a queen there. Okay? What about over here? Well, I'll check up to my left. Oh, there's a queen there. Okay, can't go there. What about over here? Well, I check up to my left. That's empty. And now I'm out of bounds, so up to the left is good. What about back to left? Empty. Okay, I'm good. And what about down and to the left? I'm good that way. So I'll go ahead. That space is a valid place. I'll go ahead and put my queen there, and I'll call the next one. Can I put a queen here? Empty. That's a queen, so valid is false. What about this way? I'm sorry, well, I don't have to check anything else, so because I already found one case where that won't work. What about here? This won't work, that won't work, and that won't work. So we try, so for this row, sorry, for this column, column 2, we tried all the possible choices. Okay? Clear any possible choices. We make sure that basically if there was that's useful for Sudoku, basically, to remember that's there. But at some point, if you know you can't go there, you're going to need to remove that choice you have. So we've entered nothing here, so I return false. Now back over here in column 1, calling solve on column 2, that just got false, so I go on to the next one. So this if statement terminates. This if statement terminates. So we're back in the for loop, so we know to move our queen down by 1 because that didn't solve the puzzle, right? So that path led us to a dead end, so we backtracked. That's what the return false does. So we're here, we put down a queen here. Can I put a queen here? No. Yes, over here. So we call the final row. No, 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 no. Return false, right? We're back here. No. So we unmark that queen. No, no. Return false. Okay, so now we're back in column 1. That got us to another dead end, so we move it for each possible choice here. Well, we just went through all 4 possible choices here. So we return false and go back over here. So now we move this queen down. Right, everybody following so far? So queen can't go here, 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 but the queen can go here. I can put a queen here. And over here, can't put a queen here, here. I can put a queen here on the other hand. And so now I call column 5. Now column 5 is out of bounds. That's a position that indicates there's nothing left to solve. Or sorry, that's column 4 rather. Column 4 says that there's nothing left to solve here. So we return true. So column 3 just got back true from this solvable, from trying to solve column 4. So it's going to return true. So column 2 just got back a call from column 3 that was true. So it's going to return true. And he just got a call back from column 2. Sorry, from column 2. So column 1 is going to return true. And column 0 got a return true from solving 0 plus 1, right? So it's going to return true. So these true calls just cascade back. Okay? So you might be asking yourself, where do I start if I need to code this up? Right? Now, the way I would do it, because I know, is that I like to build these things from the smallest components up. And what I would do is that I would start with, let's say, 8 queens. Where I would start actually, if you're stuck somewhere, is I'd start somewhere pretty simple and straightforward, which would be public static void, public static boolean, the valid method. I wouldn't start with recursion. I'd start out with basically taking in a board, right? Taking in your chessboard. Board, int row, int col. So here we want to take in a row and column for where we want to put a queen, right? A particular row column combination we want to put a queen. And we're going to throw it through a bunch of checks, essentially. And if it can get by all of our checks, we're going to return true. And what we're just going to do is that basically then you can test it out to make sure it's working, right? So what I'll do is I'll write something like val is row. So let's see. I'll write something like is same row. So, or rather, is row valid. That's a good name. Which is just going to look for to check and make sure there's not another queen in the same row. So I'll break it up rather than doing multiple checks. Rather than trying to make a big method where there are lots of things to go wrong, I'll have this method call one for each of those 3 checks I need to do. One to the upper diagonal, one to the lower diagonal, and one to the row. Checking the same row is the easiest one. And if I can get this done, then I can move on to the 8 queens stuff and then add the diagonal all later, or I can finish up these things and finish up testing this one and then move on to the recursion knowing that my valid works, right? So is row valid, we'll take in the board, the row, and the column as well, right? And what we'll say is if we get a false from there, we'll return false, right? So now we have to actually write it. So let's see. Public static Boolean is row valid, which will take in, of course, the same arguments. Int board, int row, int call. Right, we'll take in the same things, and all we have to do is check basically to make sure that we're in the same row. So I'll have a return true by default over here. Right? Basically, I'll return true if I don't see another queen. And if I see another queen, I'll immediately return false. And I'll use zeros to indicate the presence of no queen and a 1 to indicate the presence of queen. So what we'll do is that we'll start at, and we're going to write a for loop here. So for int, let's see, int I is equal to, let's go actually and go ahead. And this will be a bit of an unusual loop. I'm going to start by basically, if I'm checking my queen, let's go ahead and just do some erasures. If I've got a queen over here, I want to check for other queens. I basically want to start my checks from over here and go only until I'm out of bounds. Once I'm out of bounds, no more checks, right? So I'm going to start from, this is actually kind of an unusual way to write it, but I'm just trying to show you that at this point you can start twisting for loops to do whatever the heck you want. So for int I is equal to 1, I plus plus. Basically, I like to write those end parts first to let me know what I'm going to do with it. So what I'm going to do is that I'm going to basically, since I'm going to the left, I'll keep subtracting. So this is my same column, same row, but the column is -1. Then this column is -2, right? So what I'll say is call minus I is greater than or equal to 0. So while the column minus I is greater than or equal to 0. So notice how that's not going to go out of bounds, right? If board row column minus I is equal to a 1, if there's a queen there, return false. And that's it. Actually, the trickiest part of this, from what I've seen other students do, is basically trying to come up with good for loops, because a lot of times you'll go out of bounds or you're not checking the right things. So with this, basically, we can just at least make sure that if we go into the recursion, when we do the solve method. So, and the next thing you want to do, of course, is test it. So I'll show that in a second, how do we test this. But at least we know now that with our this, if this is working, then we could get at least an answer that's not correct, but one that we could show would work recursively by basically saying, okay, I'll put a queen here. I can't put a queen here because there's another queen in my row already, but I can put a queen here because there's not a queen in this row, right? And then I can do the same thing over here. Can't put a queen here, can't put a queen here, but I can put a queen here, and so on and so forth, right? I can do that, right? Because you always want to start from checking up here so you don't miss any possible open squares. So now what we have to, so if we know that works, then the recursion will work, and then we can go back and make sure the diagonals work. So how does the solve method, so how do we test this first? Well, first we have to create a board. So we'll do that in main. We'll build it all in main. Public stack void main. And if you're using NetBeans or IntelliJ, you can just type in PSVM and hit tab, and that'll auto-complete. That's how I do that magic. So next is we'll make our array board, and here I'll just define it literally. Right. So what I'll do is I'll have a row here, and then 0, 0, 0, 0. So 4 zeros. That probably took me longer than just typing it out, right? Then we need commas. Okay, Control C, Control V. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So now we just simply line that up a bit better. Remove the comma on this one. Right? The hardest part about this part is actually just making sure that it's lined up all correctly. So here I've actually got a chessboard here. Let's see. Oh, and I have to put an end of line character over here, right? Because that's what the semicolon is used for when you end an actual line, right? That's how it knows we're done creating a variable. Now if I want to do that, what I can do is I can put a 1 here and a 1 here, right? I can put some stuff, I can put some 1 somewhere else here. And then to test this, I'll just simply say sout, is it valid board? Now I need to give it a row. So let's check row 0, and we'll say, let's put column 3 in, right? And that should say false, right? You shouldn't be able to put something there. Okay? So false. I can't put something there because there's already queen there in that same row. What about row 1? Right? It'll say true because I can put a queen there since there's not one in that row. What about 0, 1, 2, 3? So if I try it from 0, 1, 2, 3, 4, row 4, interestingly enough, you might think it should return false, but it should return true because this is row column over here. We just passed in this. And we're only checking the spaces to the left over here, right? So it's good to know the limits of your checks, right? We're only checking behind this, right? So we're checking the 3 squares, right? Which is the desired behavior we want. Okay? So now what we can do is that you can add in the upper diagonal check in this same statement. Like you can put in and for the upper diagonal and then the lower diagonal and make sure those get taken care of. But now you have enough to go on to know that you at least can write the recursive function. So public static Boolean solve. That takes in the board. Int, whoops, keep hitting P. So int board, and again, what we're going to be doing is we're going to be solving it for a particular column. So how do I know when I'm done, right? Let's go ahead and go to the document viewer. I know I'm done when we're at when our position is over. So assuming this is a square board, I can just go if call equals board.length. And this allows me to, test it on like a 4x4 board or a 9x9 board or whatever size I want. Return true, right? If my column is equal to the length of the board, that means column is now out of bounds, so we're good. And then otherwise, by default, right, is backtracking, so we return false there. Right? If we got to the end, great. Otherwise, return false. The next thing we need to do is if document viewer, for each possible, not an if statement, but for each possible choice. For I, so we'll do for int I is equal to 0. I is less than what? Well, we have 8 things to check. Again, we're going to assume that this is a square board, right? Board.length. So this will go through this. So this will basically give us, and instead of board, we'll call it row. So right, this is all the possible rows, right? So all I'm doing is just translating this function into Java, right? If valid board row column, you mark the position with that choice. So what does that mean to do? What do we do here then? If it's valid, what do we do? How do we put down a queen? Sorry? Yeah, you just simply say board row call is equal to 1. And then what I'll do is that if I don't get to the end of this, I'll just put it over here to pick up the queen. Row call equals 0, but that's only if putting that here depends on, like, I put that here because my row is not over here, right? It's over here. Okay. So board row column, and then you have the recursive call yourself, right? solve board position +1 is equal to true, so I can just okay, so I can just copy that over, right? And it says, it's reminding me that it's column over here, so, and that's essentially it for the recursive call, right? Like I said, I mean, normally I don't code things up for you like that, but it's a very direct translation, right? The translation is brutally direct for this. I'm not sure if I've overviewed stuff here, but let's go ahead and just check it out, right? So I can do solve board 0, right? Start at 0. And then what I can do is I can print out the board, which is actually a bit tricky. What you have to do is for each integer array int row in our board, right? For every row in our board, we actually have to print. Let's see, sout arrays dot toString row. And that should show you that diagonal. Now let's see if we got it. Of course, this might actually not work because, oh, interesting how that worked out with the queens already placed on there. So let's go ahead and erase and give it a blank board, right? And you'll see that we've got this, that basically it's working for the diagonal, right? So now you've got basically those checks to make. Now normally I don't do this much for you guys, but I did get, I'm not sure how many I had the announcement on, but what my general rule of thumb is that for every single student who asks for help, multiply that by 5, and that's the number of students who actually need help. So that's generally the way it works out. Not sure, and that's a completely unscientific estimate there. So all that's left here is to make sure that you've got the upper diagonals and lower diagonals working. Okay. So, which I'm not going to do. But now let's just talk about the Sudoku puzzle in a bit more detail. The Sudoku puzzle, right? That one is, again, I've went over the rules of Sudoku in the video, right? So here, position is, for Sudoku is, you pass in two variables, the row and the column. You need an if statement here just to make sure basically did we finish the puzzle? Then you might need then since Sudoku puzzles are partially filled, you might want an if statement over here saying, hey, if I've already got a filled square, go on to the next square. And so, right, so that's kind of a base case there. It's not so much a base case, it's kind of this weird midway point between a recursive case and a base case, right? It says, oh, that's pretty simple. The next step is to move on to the next square, right? Recursively call the next square. So if you've got an empty square, you try each of the numbers 1 through 9 until you get one that fits, right? So there, your is valid choice is, gives you the, basically, again, you'll want to check, okay, is there something in the same row, the same column? And here you'll have to check both, basically your 4 cardinal directions. You don't have to worry about your diagonals this time, but you're going to have to worry about that 3 by 3 square, which is, again, a bit tricky. So my suggestion is, again, code up the is valid first, right? Check to see is there already a number of in the same row? There already a number in the same column, right? Same row, same column, right? And then at the end, worry about trying to solve it for the 3 by 3 square. Okay. So if you try to solve, and then once you can do that with solving it for those 3 by 3 square, then it will produce the full puzzle. And again, the way the 3 by 3 square might work is that I highly recommend experimenting what happens when with indices for dividing by 3 and moduloing by 3. That's my hint there. Because the easiest way I found is that for a given square, in Sudoku, you want to find out what the top left corner of that particular 3x3 is, right? What the top left corner of that 3x3 is, and then you just go through like the first 3, then the second row of 3, and the third row of 3. And you can find that out by just doing some interesting division and modulo to figure out where your original space was.